Welcome to Exploring Computing. Today's video is Computer Theory, Undecidable Problems. So one question we might ask ourselves is, are there limits to what we can actually use a computer program to compute? And the answer is yes. Some problems are undecidable, and we cannot write a computer program that can solve these problems. One famous example of an undecidable problem is the halting problem. Now, one thing that we often use when we're developing computer programs is we use computer programs to help us write computer programs. So you kind of think of like if you use an editor with syntax highlighting, what we're doing is we're taking the computer program that you're writing and we are using a second computer program that is analyzing that program and figuring out how to do the syntax highlighting on it. So similarly, a compiler analyzes computer programs and determines if they follow the rules of that computer programming language. So one question is, it would be pretty useful if we could write a program that determines whether or not a program will actually stop running for a given input. If I write a program, can I say, hey, if I have the following types of inputs, will I ever run into a situation where I accidentally have an infinite loop? Can I analyze the program and determine that this situation will never occur? And so that's the halting problem. So we're going to prove that you can't actually write a program that will be able to determine whether or not a program halts for a given input. And we're going to prove that this does not exist by contradiction. So the way these proofs by contradiction works is we're going to assume that the solution to this problem actually does exist. And then at some point, we're going to see that there's a contradiction and that our original premise that the program existed must in fact be false. So here's our little program here that does actually work, or we're claiming it works. We're claiming it could exist. And so you can see that our program takes a couple inputs. One of the inputs is the program that we want to analyze. And the second input is the data that I want to run on that program, which we're analyzing. And so I tell the program, the halting program, hey, here's a program I want you to analyze, and here's some data that I want to feed to that program. Can you look this over and tell me whether or not this program is actually going to stop for this input? And so this should output true or false. So I'm going to claim that this program does exist. And now what we're going to do is we're going to modify this program by, adding a little bit of extra code here. So I'm going to say, if that original program, which tests for halting, returns true, I'm going to send the program into an infinite loop. So, that's easy enough. It's just like, while true, go do nothing. And that's an infinite loop right there. Okay, so if that original program testing for halting returns true, go into an infinite loop. Otherwise, if that program that determines whether or not the input will halt for a given data input, then I'm going to go ahead and stop. Now, what happens when we run the program on itself? So I'm going to go ahead and take my extended halting program with the extra infinite loop test on it as input. So that's the program we want to analyze. And then I'm going to say, I'm going to ask that program to analyze. And then as the data I expect that program to analyze, I'm also going to use the exact same program. I'm going to say, it's going to analyze this halting program with the infinite loop added to it as data. And then we're going to go ahead and carry out this analysis. So let's look at what happens here. If the original analysis program concludes that the extended halting program halts on its own code, then that original program is going to return true because it says, this will in fact halt. But then we added in that extra code that tosses it into an infinite loop. So that's kind of a problem because we just said that it was supposed to stop, but in fact, it's entering an infinite loop. On the other hand, if the halting program original analysis program concludes that the extended program does not halt on its own code, then that inner original test program returns false. And this extra code we added says if it returns true, go into an infinite loop. Otherwise, if it doesn't return true, stop. And so, in fact, the program stops. But our analysis concluded that, in fact, the program doesn't halt. It goes into an infinite loop. So you can see we've got a contradiction here. Either we're wrong because it goes in an infinite loop, or we're wrong because it halts. Either way, our halting program analysis, our original halting program analysis is not working. And so therefore we can see that we cannot in fact write a halting program. So this is just probably the most famous example of an undecidable program. But the main reason why I wanted to cover this was just to, sort of emphasize that I'm sad to report that computers cannot do everything. And that actually seems like a good place to end our lecture. So I hope you all enjoyed the class and you all learned a lot. Good luck with your future endeavors.